All right, welcome back to ECE484, fall 2021. Hope everything is going okay. All right, so today we're going to finish our discussion on nonlinear systems. Like I said, we are just barely scraping the surface on this topic. We will not cover all the material in Chapter 5 of the course notes, and you're not responsible for the material that we didn't cover, okay? Some of that material could potentially be useful for the lab, but you will not be tested on it, okay? So just keep that in mind. In terms of Chapter 5, follow the spreadsheet that's on Learn to see which sections of the notes are fair game. Okay, so last time we were talking about control design based on linearization. So this was the idea where you approximate your nonlinear plant using a linear model near an operating point or an equilibrium configuration. You design the controller for the linearized model, and then you use it to control the original nonlinear system, okay? And the most important point of what we discussed is the picture shown here, right? So this is a picture of how you would then implement the controller that you've designed on the nonlinear plant, okay? So you should understand what this picture is about, okay? So the thing to take away from last class, one of the things to take away from last class is this: what is this picture showing you? What is it about, okay? You should understand what this picture is saying, okay? And the basic idea, again, is that you have to introduce these biases so that you are close to the operating condition. And if you go to simulate this system, you need to make sure that your nonlinear, you want it to work reasonably well, your nonlinear system that you're controlling should be initialized either at the equilibrium or nearby, okay? If it's not, then you wouldn't expect the controller to work that well. So keep that in mind when you're simulating or testing in an experiment. Then we started talking about a kind of a different conceptual idea, and that is this notion of kind of canceling out or inverting nonlinearities. And it's conceptually very different than what we did before, but the outcome is sort of the same. So conceptually it's different because we're not doing an approximation here. What we're trying to do here is to invert the nonlinearity of at the input of an otherwise linear plant to be able to use linear design methods, okay? And so here's a picture of the type of controller that you would get using this approach. And the basic idea is that you select this kind of block here in your controller. And by the way, this is the example from the notes, which is kind of slightly different than what we did in class, but the idea is the same. So the idea is that you would select this nonlinear block here so that when you compose it with the nonlinear block at the input of the plant, those two blocks cancel out. And so that's what I've written down here. So if selected properly, so in other words, if this block is selected properly, then what you'll get is that W and V are equal. It's as if those nonlinear blocks did not exist because you've canceled them out perfectly. And then you end up with a linear closed loop system. Okay? So the advantage of this approach is that there is no approximations, right? We're not approximating a nonlinear system using a linear one, we're just canceling. The disadvantage is that you need a good model, right? In order to pick this block, I need to know pretty well what this block is, right? I want them to cancel out perfectly or reasonably close. So it might be less robust than design based on linearization. Linearization, of course, you have a model, but once you put that model in feedback, you end up getting the robustness. Here, we are sort of sacrificing a little bit of robustness, trying to do this perfect cancellation. Okay. So that's what we did last time. We're going to continue from there. And the next example we're going to do is sort of the, in some sense, opposite scenario. So instead of having this nonlinearity at the input of your plant, suppose that it sits at the output. What do you do in that case? Well, you can imagine we're going to do the same sort of idea, except now this block that we've designed, instead of being right there, it's going to be somewhere down here. So that when this nonlinearity from the output hits this block, they cancel out. So let's see how that looks like in an example. And by the way, this is something you've already done in the lab. So let's do an example. Of a nonlinear sensor. Okay, so this is a block diagram that you know quite well. Let's see. Let me see if I can do something here. Okay. So suppose that we have our, our standard DC motor. Okay, and to measure the positions, we have an encoder measuring the position of the shaft, right? And that encoder is turning the angle into a voltage. And let's say that that conversion ends up being nonlinear. So I'm going to draw it this way. Okay, and let me fill in some of the various signals and systems in this figure. Okay, so the input, as always, will be U. The thing coming out of that plant block which I'll write this way. This is a sort of model of our DC motor. And the thing that we're actually reading, the thing that's available for feedback, is Y. And we're going to assume that it has a sort of slightly nonlinear, very mild nonlinear form. Something like that. And this is our sensor. Okay. What do we do in this case? Right? So this looks like a linear system with a nonlinearity, a static nonlinearity at the output. Okay? So again, kind of the opposite of what we saw last class. So let me write that down. This is happens to be linear system with a static nonlinearity. Okay, and I'm going to use the same notation we used last class. So last class we used this capital phi symbol for our static nonlinearities. So static nonlinearity in this case is going to be the expression for that sensor, okay, at its output. Right, and as if you remember last class, we had these two pictures. There was one where it was at the input and one where it was at the output. We're dealing with the output case here. Okay, so in this case, the function is invertible. It's left invertibility is what we really need, but in this case, it's actually invertible. So the question is, why is it nonlinear? So if you remember, what is the definition of a linear function? A linear function satisfies additivity and homogeneity, or in other words, superposition. So every linear function must pass through the origin, right? So, fundamental question. When you draw the graph, it's a line, but it is not linear. Linear functions pass through the origin, aside. F from x to y is linear if definition of linearity, superposition. Okay? So if you choose, so that has to be true for all x1, all x2, all alphas 1, all alpha 2. Okay? So choose alpha 1 equal to 1, x1 to be whatever you want, alpha 2 equal to -1, and x2 equal to the original x you chose. And you will see that f of 0 must equal 0. It's the property of linearity. F of 0 must equal 0. It doesn't pass through the origin, not a linear function. Okay. So in this case, the function is invertible. But it is mild nonlinearity, right? It's not very severe, but it is nonlinear. The function phi is invertible. And so we'll choose the symbol we were using last class, and we'll use it again for our inversion, is capital psi. So in this case, it's this thing. And so when we compose these two functions, we get the identity function. Okay, so so that's the idea. Basically, we can implement this easily on a computer, this psi function, no problem. And so we'll take y, we'll run it through this psi function, and then use the result, the output of that psi function for feedback. So use psi of y as the signal being fed back. Instead of y. And if we do that, we'll have a linear system. From u to psi of y. Okay? Essentially, this little argument we're seeing in this example is why we often talk about unity feedback systems. And when I draw the block diagram, you'll see. Okay, so let's draw the block diagram. So we have our, let's see if I can draw this. Okay, so here this will be our plant, the usual story. Well, a plant with the sensor. So B0, this we said was K theta plus Y naught. All right, so we have that. And then our controller we'll design, the usual way. And here we'll have our inversion. So this will be C of S. This will be 1 over K Y minus Y naught. And that signal is what we're going to use for feedback. And so the rest of the block. Okay. And so I'll draw the block around our controller. Okay, so there's our controller. And of course now, let's label some of these signals. Theta, Y. Now, of course, because the thing you're coming out of that inversion block is, hopefully, if we've picked the constants properly, it's theta. We have to make sure that this is theta ref over here. Right? So that's the basic idea of inverting something at the output, right? And again, this is something you've done already in the lab. And by the way, look at this picture. If we've done this inversion correctly, right? If we've been able to pick K and Y naught, right? We've done the correct inversion. We have a unity feedback system. It's as if these two blocks were not there. And indeed, that is why we pay so much attention to unity feedback systems, right? It is kind of implicit, this idea that whatever the sensor provides to you, you will turn it back into something meaningful, right? In this case, angular position. So ideally, if these cancel out, you end up with a unity feedback system. And this is why we pay so much attention to those, right? Okay, and now you design C of S in the usual way. All right. So just like we said for cancellations at the input, let's look in a little bit more detail at this cancellation that we did in light of the fact that this is going to be implemented on a computer. So in reality, there's going to be a sample block sitting in between here, and this is all going to be discrete time on this side. Okay? What does that mean in terms of our implementation? So this is remark 532. Implementation on a computer. Okay, and I'm going to basically zoom in on that block, the cancellation part of the above block diagram. Okay, I'm just going to zoom in on that cancellation part. And so I'll remind you of what that looked like. Okay, so we have these three blocks. Okay, the first block is the nonlinearity from the sensor, so let me write that out. This is our sample block. And then, of course, the inversion will occur. We're going to implement it on the computer, and so this will be our inversion over here. Okay, so this, of course, we said was theta of t. This is y of t. And if we've, in the way I've drawn it, right, we have the same k and the same y naught in both blocks, so this will be theta of k. So what we will get is that theta of k is going to equal theta of t, right? Exactly at the sample instance. Of course, theta will change in between samples, right? Theta will be changing. That's not going to get reflected over here. But at least at the sample instances, we get the cancellation, okay? And again, the reason this works is because the nonlinearity is static, right? The value coming out of this block at the sample moment only depends on the value of this block, or this signal, at the sample moment. It does not have history or dynamics, right? If it was a dynamic nonlinearity, then it would not be true that the value theta at the moment we sample is equal to this value. Okay? So let me write that out. So theta k equals theta kt at the sampling instant since the nonlinearity. Is static. Okay, if it was a dynamic nonlinearity, this wouldn't work, right? You wouldn't be able to pull out the value of theta, sampling just the value of y at that moment. Okay, so that's end of section 5.3. As I mentioned, I would argue that the ideas presented in that section are sort of intuitively what you would do anyway, right? Like, it's not like, you know, I spent the time in lectures talking about, but intuitively, if you were confronted with such a system, this is something that most people would probably think up on their own, I would imagine. Okay, so in general, just make a comment here. In general, more care is required when trying to cancel dynamic nonlinearities. Okay. This is, if you've ever taken robotics, if you've seen robotics courses, in robotics they would call this, when you do these cancellations of nonlinearities, they would call it computed torque control. In nonlinear control systems, they would call it feedback linearization. Okay? But basically the idea is the same, canceling out dynamic nonlinearities. Now you can do it, but there again you're going to require fast sampling for it to work well. Okay? And so I'll just see an example. Okay, so that's it for section 5.3, very brief. And now we move on to even briefer section, static friction. If you don't already hate it, by the end of this lab, you're going to hate static friction. It's going to be the bane of your existence in trying to get your lab to work well when you go to implement, right? Right now, you're still working on simulation models. When you go to implement your controller in the lab, you will realize that static friction is a real killer when it comes to performance. So let's make a few comments about it. It's a common nonlinearity. That can make control design challenging. Okay. It is very hard to model. Okay, so if you look in the notes, I give some discussion of ways you could try to model it. And while that discussion is going to be more complicated in the notes than what I say in class, it's still a crude model, right? People are still writing papers on trying to come up with good models of these static nonlinearities. Okay, so it's hard to model. It's time varying, right? You run your controller, and say you get your controller working in the lab today. We're in the fall. If you come back and try it in July, static friction is very likely to have changed, right? It depends on the temperature, the humidity, right? It's time varying. So it's a difficult time varying nonlinearity, and so it makes it hard to model. It's also problematic. Okay, so in terms of control, it can lead to increased steady state error, right? So you think that you've got an integrator in your controller, you should get perfect steady state tracking, and in steady state, your control signal should settle to 0, right? If everything is going well, because you're gonna have 0 tracking error going into your controller. Well, what happens with static friction is that when you start to get close to 0 in your control signal, static friction basically makes the system stop moving, right? Because you're applying very small control signals. The system is essentially stationary, and it stops moving. And this results in steady state error. So it can increase steady state tracking error. And it can also lead to oscillations, right? Because if you have this integrator, you accumulate some error over time through the integrator, then you start to apply a big control signal because your integrator is wound up, so to speak. You apply the control signal, you overcome the static friction, and the system moves suddenly. Okay? And what this will happen is that it'll overcorrect, and it'll try to overcorrect again, and this will result in oscillations. And in extreme cases, it could lead to instability. Okay? And so the method that I'm going to discuss here is, again, the one that you would have tried in the lab. Because it's, over the years, that's the one that's worked best in the lab. But, if you want to look in the notes for other approaches to dealing with static friction, certainly that's an option for you. But I'm going to talk about essentially applying the ideas of inversion from section 5.3 to static friction. So a crude way to model static friction is to model it, or it is as a so-called dead zone nonlinearity. Okay, and so what is that? We're going to draw it in a moment, but that's a static nonlinearity that is right invertible, and it appears at the input of our system. Okay, so the basic idea is that we crudely model static friction as a static nonlinearity. It's not, but that's the crude model. And then we do the inversion idea. And then apply. the inversion approach. Of section 5.3. Okay. So what is a dead zone nonlinearity? Okay. As usual, we're going to write U over here. It's going to be our dead zone. Capital Phi is, again, the symbol we've been using throughout. And again, you've seen this in class or in the lab, but it's basically there's a period in which the input has no effect, doesn't show up. So small values of U result in 0 output. And eventually, when you overcome the static friction, U starts to show up. Okay. And so the slope here is 1. And we will call these points where the slope goes from 0 to 1, the points of non-smoothness. Call that U plus, U minus. Okay? And so the model that we're going to have is the following. So the input will be U, as always. Output Y. Here we're going to have an otherwise linear system. And here we have our dead zone nonlinearity. Okay, and this block here becomes our plant model. Okay, and so again, this is a crude model of a linear system with static friction at the input. So this is a crude model of static friction at the input of an LTI system. Okay, and it has its drawbacks, this approach, but it has some advantages too. And one of them is that the values U plus and U minus are easy to measure, right? This is something you would have done in the lab. The values U plus and U minus are easy to obtain experimentally. Though again, it's time varying. So it might be that when you finally go to implement your controller in November, the values that you have for U plus and U minus in the lab may have changed. So you may have to recompute them. So keep in mind, though they may change over time. And the other nice thing about using a dead zone nonlinearity is that it's invertible. It's right invertible, so we can use our previous ideas. And the dead zone nonlinearity is right invertible. Okay. And so what does that inverse look like? It looks like something like this. Okay, so our usual symbol has been psi for the inverse function, and so I'll draw it like this. Okay, so that's the inverse. Okay, and so the idea then is, just like before, we have this block. So the second block diagram that was shown in this lecture, where we were canceling a nonlinearity at the input of a plant, we do the same thing for our crude model up there. So let me copy that. And then show what our controller idea would look like. Right, so our controller would look like this. Okay, and this is the signal that we will design for, right? So W now is the signal that your control block will produce. Okay, and ideally, well, certainly this will cancel the dead zone, right? So if it were indeed true in reality that static friction was a dead zone nonlinearity, then this cancellation would be perfect. Oops. And you'd be off to the races, linear system. And of course, this leads back to the drawback of this approach that I mentioned at the start of this lecture. The drawback of this approach is that if this is not a good model of the nonlinearity, then this will not be a good cancellation, and your closed loop system will not appear to be linear. Okay, so again, I'll reiterate what I said at the start of lecture. Cancellation is nice because it doesn't require approximation, right? So you in principle could get larger regions where this controller will work. The linearization-based approach that we've talked about at the start of this chapter relies on approximation. And so the region in which it's going to be effective is smaller in principle. However, because you're using feedback around your linearized model, it tends to be more robust. So you're trading off a little bit of robustness for possibly larger regions where your controller is effective. Okay, so in principle, like I said, y of s equals g of s, w of s, and the control signal u, or w, can be designed using linear methods. Okay, and that's all I'm going to say about static friction, right? I don't have the magic solution for static friction in the lab. That is probably the best one. It's the one that works, but you might have to do some tweaks. There are other approaches in the course notes, but I'm not going to spend time in lectures talking about them. Okay, so we now really, I kind of mentioned this before after the end of chapter 3, I think, but now we really move on to discrete time systems. Okay, let's recap what we've done so far. We've come up with a new continuous time design method, pole placement. We talked about emulation, so discretizing continuous time controllers and implementing them on hardware, on digital hardware. We now move to the second main approach to digital control design, and that is where you design the controllers in the discrete time domain, right, or in the Z-transform domain. We leave the continuous world behind, and now we start to work in the discrete time world. Okay, and so in preparation of that, we're going to do a very quick recap of discrete time systems, and that is chapter 6. Okay. So the flavor of the course in some ways changes at this point. Chapter 6, discrete time. linear systems. Okay, so I'm assuming that you have some background in this material, but I'm going to go relatively quickly, but nevertheless we'll review some of the main important ideas. Some of the material in this section, in this chapter will be new though, but that comes later on. 6.1, difference equations. We saw them in chapter 4 when we were discretizing continuous time controllers. Let's talk a little bit about them in more generality. So it's a common way to model discrete time systems. Okay, and I will generally write my difference equations in the following form. Okay, so yk plus a1 y of k minus 1 plus dot 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 an y of k minus n equals b0 u of k, and so on. Okay. So what's going on in this equation? Well, k is time, of course. It's the discrete time, the independent variable in the equation. So k is an integer, the discrete time variable. Okay. Y is the output. Right. You can think of it as a sequence, right? It's a sequence of numbers, real numbers. And u of k is the input sequence. Okay. And you've seen probably very simple examples. Certainly we had some examples in chapter 4, but let's mention a couple more. First is the delay system. So, one-step delay. Okay, so what does the system do? The output at any given moment in time is equal to the input at the previous time, in discrete time. So it's a system of the form above, where a1 to an are all equal to 0. b0 is also equal to 0. b1 is equal to 1. And the rest are 0. So I guess I should mention that the ai's and bi's, we assume, are real numbers, okay? They're just constants. Okay. Now there's another system we could write here. Which does not fit the form above, right? This is not an instance of that general equation above. It's actually a non-causal system. Right? The output at time k depends on the input at the next time step. Okay? Now, in this course, we will not study non-causal systems because we are doing real-time control, right? Our algorithms, our controllers have to process information in real time. They don't have future information. If you're doing a digital signal processing course, where you are taking information offline and then processing it offline, then you can consider non-causal systems. But for us, we're going to focus on causal systems. So for us, that's the kind of system we're going to look at. Okay, so again, this is not an instance of the above. Okay, let's do another example. Question is there a branch of controls that does predictive control to do semi-real-time control with non-causal systems? Well, okay, so non-causal systems just don't exist in, like, the systems themselves. Like a physical system that you're trying to control will always be causal. So I can't think of a real life system that is non-causal. The non-causal systems that I'm aware of are offline signal processing. Okay, and then the question of predictive control. Well, yeah. So, someone else has asked me about this, right? We don't cover it in this course, but one way to get around this issue of you don't have future information is that you take all the information you have up till now. So remember, control, feedback control, sense, compute, actuate. So you sense, you try to get a feeling of what the state of the world right now. At the computation stage, what you could try to do is predict the future. Okay, but it's a prediction. You're not using real information about the future. You are predicting. And that's called model predictive control, or that's one type of control. It's called MPC, model predictive control. But it's a prediction, as you write. It's not, you don't actually know the future information. You are predicting it. So it still remains causal. It's not using future information to make a decision right now. It's just guessing as to what the educated guess, but it's guessing to what the future information will be to make a decision right now. So it remains causal. So prediction is not non-causality. Prediction is prediction. You're using what information you have now, which means you're causal, to predict about the future. You're not using actual information about the future to predict, to make a decision now. And so in real-time control, it just doesn't happen. Again, it happens in offline signal processing. So I record my voice, I sound like crap, I want to make it sound better. You can, change the tone of my voice at this second using future information of that recorded voice because you have it all, right? It's on a tape, or, sorry, I'm old. It's on on your computer, and you can do non-causal filtering of my recorded voice. Okay, so that's a bit of an aside. So to answer your question, I don't consider prediction. Prediction is not. It is causal still, right? Because again, you're using information you have available now to predict about the future. You're not making decisions now using actual information of the future. So a moving average. So this is something you've probably done, right? You've played around with an Arduino, you're getting sensor information, it's a bit noisy, so instead of using the sensor measurement you have right now, maybe you take the average of a couple of sensor measurements and you use that for your algorithm, whatever you're doing. Okay, so in this case, let's say we take a 5-point moving average. Okay, so again, you take your 5 previous inputs, your current input plus the previous 4, and you take their average, right? So it takes the average of the 5 inputs. There's an example, okay? So the output at time k is the average of the last 5 inputs. Okay, and of course you can change the number of points you want to take the average of. So you could do a 20-point average. So now consider a 20-point moving average. Okay, so that's fine, we can do this. But now if you want to take a 100-point moving average or a 500-point moving average, we have a bit of a problem here, right? It starts to get a bit more and more memory intensive. Here I've got to store, in order to compute this 20-point moving average, I have to keep in memory UK minus 19 all the way up to UK minus 1. I have to save these 19 previous values plus the one that I just read from the sensor, right? So is there a more efficient way to implement this algorithm? And the answer is yes. So instead of storing the past 19 inputs, in memory, consider the following. Take that 20-point moving average and subtract 1 from all the time indices. Okay. Now, take y of k and subtract it from y of k minus 1. Or say, subtract y of k minus 1 from y of k. Then y of k minus y of k minus 1, so it looks like what we have up there. Oh, if you use past information list, couldn't the data by various state therefore not a good indication? Yeah, of course. I mean, the application will determine what average you want to use, right? You know, this, of course, the way you would choose this, of course, probably would be depend on frequency domain methods, right? And we'll get to that, right? You'd try to look at the frequency content of the incoming input, and that would probably just help you decide how many points you want in your average. Okay. Yeah, but yes, that's right. I mean, the application would tell you how many points you want to average. Okay, anyway, so if I subtract y of k minus y of k minus 1, what do I get? I get and I argue that's a much better implementation, right? I only need to store the previous output and the input 20 time steps ago. So I now only have to store 2 pieces of information. And that's true no matter how many points I want to take the average of. So better for implementation. Okay, so difference equations, a common model of a discrete time system. So now the question, of course, arises, if I have a difference equation, how do I compute the output? If I give you an input sequence and maybe some initial conditions, how do I actually compute the output? So given an input, sequence, and some initial conditions, how do we compute the output? So of course, one thing you can do, obviously, is just do recursion. Just recursively compute y0, y1, y2 until you get to the value of the output that you're looking for. You generate the sequence. And that's what this next example will be about. I probably will not have time, but we can get started anyway. Okay, so I'll just write down the example and then you can think about it. So there's our difference equation. And let's say that our input is, or say we know that y of negative 1 equals 1, and u of k is the ramp. So if I give you that information and I ask you, what's the output of this system? One thing you can in principle do is you write a big for loop. I tell you, okay, I want to know y 300th value of y. You could write a for loop and you could compute y of 300. Okay, and that's what this example will discuss. And then we'll talk about maybe there's a better way to do it. It doesn't require this recursion. And we'll do that next class. Okay, so that's it for today. I will see you guys tomorrow. I'll stick around for a minute in case there's a question. I might not have time to do that in very much detail here, but you have a linear system with in this case, we called it a nonlinear sensor at the output, right? We, in this course, and in all of undergraduate, essentially, deal with linear systems. And so we would like the closed loop system to look like a linear system. And so the idea is that on our controller, so this is kind of the plant in some sense, right? It's the plant plus sensor. Repeated over here, plant plus sensor. So what we do in our controller is we take the output of the sensor, and we try as best we can to invert this function so that ideally this signal coming out of our cancellation is theta. So ideally, that's the same signal. Okay? And if that's the case, then you can effectively think of this as just being gone, and this as being gone, right? As if they weren't even there, i.e. a unity feedback system. Okay, I can talk about it more next class, but unfortunately I have another class to give to your classmates, so I will continue. I can talk about it more next time.